been all very interesting. So this is everything I will present is basically the work of Corin Jorgenson, Soline, Ghinet, that Corin did the master with me. Now he's doing a PhD in our group. Soline is doing the master, and Mónica, Ágreda, López also did the master on Colli Albani, and now he's a PhD student at the University of Perugia with Maurizio Petrelli. And this is a collaboration now that is few years with Guido Giordano, that is probably 20 years working on Colli Albani, even if he's very young, of course. So today I want to speak. This is a nice picture of Colli Albani. These are some of the latest Mars that were produced by the last activity of this volcanic area. See, okay. So Colli Albani, the interest here is there are multiple. You will see it's a quite complex system with very interesting magma composition, and is located very near Rome. There are geophysical evidence that this volcano is still active, and I think there are even volcanological evidence that this is still active. There is magma somewhere in the lower crust. This has been shown geophysically. The gassing is very high. There is and the heat flux is also very high. It's comparable to some of the Mexican active volcanoes. So the magmatism in Italy, many of you will know that there is the subduction of the Adriatic plate, but the magmatism is essentially controlled by the retreat of the slab that produce an extensional region on the Tyrrhenian side, and this results in magmatism. The eruptive history of Colli Albani is very interesting. It's punctuated by some large ignimbrites. Some are 50 to 60 cubic kilometers. And this is a little bit the interesting part about this volcano, because you will see it's very mafic and alkaline rich, so very low viscosity magmas, but still very large caldera forming eruptions. And this is one of the themes we will try to address. I mean, we are probably not going to solve the problem, but a lot of people is thinking about the way we can generate such large eruptions with this magma composition. This is a schematic sketch from one of Guido's paper. And one interesting thing is that the last 3 ignimbrites at least, but it's true for many others, they start with a fold deposit, and then they are followed by the pyroclastic deposit, and then they have various degree of welding, these ignimbrites. And the activity in the middle is intercalated with some violent strombolian activity and diffusive activity. So this is the thing. These are the composition of the rocks. You see that very potassic and very alkaline and very potassic rocks, low silica content. And this is a diagram from some work of Freda and others. And you see how there is a sort of relationship between the DRE of eruptions and the silica content of the magma that feeds this eruption. And this is one of the ignimbrites of Colli Albani, and it's a little bit of an anomaly. So very low silica content, but yet quite large explosions. So the big discussion here, this is going on since a long time. I have a position on this that you will figure out during the talk, but I don't pretend to be right. I may be totally wrong. But the discussion here is that if we look at the geological map, the Colli Albani volcano is built on a carbonate platform, but we know also that carbonates have been subducted. So we have a sandwich. So we have shallow carbonate, deep carbonate. And the discussion here is, are the eruptions very explosive because there is some interaction between magma and carbonate that adds CO2 to the magma and makes it very explosive because the gas content increase? And there is a part of the community that thinks that this is related to shallow level interaction with carbonates. There is another part of the community that says, no, the carbonate actually metasomatize the mantle, and this is what produces this very weird compositions. And it's also the reason why the magma are very CO2 rich. So now this is a little bit of a problem, and I think we need to discuss, because isotopically, these carbonates are the same, it's the same material. so that is deep in the mantle or shallow in the crust, is a little bit of an issue really to distinguish between the two processes. So probably we need to take some different approaches. There's a lot of work from Conticelli from the geochemical point of view. Conticelli has the deep opinion. And I would like to discuss it with you. I mean, to me, one of the problems here is if this is shallow level assimilation, why the CO2 stay inside and doesn't leave the system? So, and how much can we assimilate? Geochemically, it seems that to explain the geochemistry of this magma, it takes about 75% of assimilation. This is an awful lot of assimilation that will lead to crystallization of magma. But these are open questions. You start to see what opinion I have, but it's complicated. This is what I want to say with this slide. I would like to start with a little introduction on thermobarometry because I'm going to use it for the later study. So this is a classic approach to thermobarometry. Is based on thermodynamics and so the pressure is function of the composition of minerals, for example, pyroxene. And in most cases, this pyroxene is coupled with a liquid. So the assumption that go behind this approach, the experiments, of course, needs to be at equilibrium. Then the end members need to be pure, or in other words, we only consider some of the components or some of the chemistry that goes into the pyroxene. And we need to be sure that the liquid we are taking to be in equilibrium with the pyroxene is actually the correct liquid. So this is the classic approach. So recently we have started to take another approach that is based on machine learning. And one of the reasons to take this approach was that we didn't want to take any initial assumption because we think that these assumptions are really strong and they could produce results that are perhaps not ideal. So we took another approach, and we are trying this now since a while with Maurizio Petrelli. And so what does it do? Is essentially it's nothing else. I mean, I can go through the detail. This is based on a ensemble of decision trees, but the important thing is essentially comparing the composition of the analysis we take of a pyroxene with a book of experiments. I imagine this to be a book that contains all the experiments that have been ever performed that contain pyroxene. And the machine learning algorithm goes through this book for us and finds the composition that is the closest, or the compositions that are the closest to the analysis we got from the microprobe. And then he said, well, these experiments were performed in this range of P and T, and he returns this range of P and T. So it's nothing really complex, but I find it nice because it's basically finding the most similar thing with experiments. That is something we do sometimes manually, looking at the experiments, the best match. This does it for you. How does it work is essentially a little bit the wisdom of the crowd approach when you have to count the number of candies you have in a bowl. Each of us is very bad at saying how many candies are inside this bowl, but actually experiments show that if you take a lot of people and you plot the distribution of the estimates, the mean estimate is very close to what is inside the bowl. And this is what random forest does. It generates a number of trees that have different structures. And then each of them returns a pressure or a temperature. And then you put all this together and you get an estimate of TNT. So I'm going very fast, but this is just an example. These are all experiments that have ever been performed that contain pyroxene. And I plot here the residual. I took the Euclidean distance. So this is the sum of the difference of all the oxides of the composition and all the experiments. And red is low and I is black of the residuals. And the diamond is the estimate we get from the random forest. And you see that the random forest gives you something that is around the minimum of this residual. So it's really looking through the book, finding the most similar composition, and then it returns you the P and T at which these experiments were performed. So some thoughts about thermobarometry in general. When you look at the calibration data sets, you see some things that are a little bit, that are like this. So first of all, obviously the experiments are done for magmas of different composition. And more worryingly, you see how pressure and temperature are dependent. And this is simply because if you perform experiments at high pressure, you need to increase the temperature to avoid that you generate a solid rock. So if you want melt in your rock because the liquidus temperature increase, you need to increase the pressure. So this dependency is something to think about, because a lot of time when we run classic thermobarometry, we start to get relationship between P and T, where we see the temperature increasing with pressure. And you think, well, this would make sense, and it can make sense. I'm just saying here we need to be careful to think if this is only a bias in our data set. So the important part about this machine learning approach is that we can estimate the error for each single analysis we have. So some of the estimates we get are really bad. So we get very large error estimates. So we may decide not to include them because the random forest is essentially telling you, I have no idea. I don't know which pressure and temperature this mineral was formed. That is very good, because at least you know that this is not good. We know what is not good. And this is very important because the estimates we get from normally are expressed as a standard error of the estimate or a R squared. And this is based on the regression of the entire data set. But you see here that there are many less experiments at high pressure than at low pressure. So the error cannot be homogeneous. And if we cannot make with confidence express the error, we don't know if we can trust an estimate of pressure that is very high, for example. So this is these are some of the difference between these two approaches, and I think they're interesting. So does it make sense that we get a relationship between pressure and temperature? And I draw this diagram to show that probably not really. So if you take a magma that contains some water, and you imagine you have is water undersaturated, and it becomes saturated here, you can imagine if a magma is somewhere here at the base of the crust on the liquidus temperature, upon ascent, it will be always overheated. So what this means, that there is no record of high pressure. This magma will simply not crystallize. It will only crystallize a shallow depth. So it's likely that if you get something that is mantle looking, it may not return high pressure. The second problem is that even if this magma crystallizes at the base of the crust, somewhere here, now upon ascent, it will also become overheated. So the probability that this crystal gets resorbed is also quite high. And this generates problem not only for thermobarometry, but also for melt inclusion preservation. So if you try to preserve a melt inclusion down here, it's complicated, because with very high probability, you get resorption. In the middle of the diagram is good, because there is no, at least the magma doesn't go above liquidus, so you may have a little bit of resorption, but the probability of preserving this composition is high. And then when you cross this 50% crystallinity line, also becomes less likely to get this, because the magma is essentially a solid rock. So these are some considerations. And then does it make sense thermally that we get a relationship between P and T? So we ran some 1D thermal modeling to show what is happening with prolonged magma injection. And what you see here is the temperature that we sample randomly our model. And you see that the temperature you get are quite straight. This is happening after a few million years of magma injection. So it's for mature system, but there is no more relationship between P and T, because the amount of sensible heat injected into the system is so high that it completely overwhelms the variation of P of temperature with pressure that was related to the initial geotherm. So P and T relationship we need to think about when we have estimates from thermobarometry. So if you get these estimates, then we go in the direction of this schematic illustration of magmatic system, where if we get straight lines of temperature and pressure, we may imagine a sort of transcrustal magmatic system. So now we go to Colli Albani, because then I will show this thing. I needed to have a little introduction. So we did field work. So this is the area, and this is the work of Mónica, Ágreda, López. What she did was to compare two outcrops located on both sides of the caldera. In this case, they are called Tuscolo and Artemisio. She did the stratigraphy work with Guido, and you see this is the section. There are some eruptions before. This is the last ignimbrite. This is called Villa Senni. There are some eruptions, then there is a paleosoil, then there is a fault deposit at the base, and then there is a sequence of ignimbrites. And then the sequence is finished, and there is some later activity. This also strombolian and small eruption. And what Monica's thesis was about was to look what happened before one of these big ignimbrites and what happened after. So she focused on the deposit before and the deposit after, and we had data for the Villa Senni ignimbrite that I will show later. So what she found that I think is interesting is, first of all, so the Villa Senni 0 is the full deposit at the base of Villa Senni. These are the eruptions that occurred before. This is the Fontana Cento Gocce formation, it's called in Tuscolo and Artemisio. This is the same unit, but you start to see difference. This is done for Clinopyroxene, and this is the eruption that occurs after. And this is the Villa Senni ignimbrite. We see these differences between these two units that occur before the big ignimbrites, also in trace elements. You see they look different, and especially this full deposit before, it looks very different from the other two, but also between them, they look different. We did some clustering on this just to identify better the difference in composition. And what you see is that almost each eruption is identified or dominated by one compositional cluster. For example, this is Villa Senni 0, then these are the two eruptions that occur before Villa Senni 0. So we are going down stratigraphy here. And so the message here is, if you take the same eruption that occurred before the last ignimbrite on two different places of the caldera, geochemically, they look different. That's the message. So we did thermobarometry using this approach on these eruptions. And the interesting thing here is, first, we see that the difference between Tuscolo and Artemisio on the two parts, these are the eruption that precedes the big ignimbrite, is that on Tuscolo we see a lower temperature extension of the estimates we have. And Villa Senni is very different. So Villa Senni 0, the full deposit, is the one that brings up the deepest pyroxene. The pyroxene recording the highest pressure, and as you see, relatively constant temperature and low temperature. So this is the characteristic of the full deposit. Then the ignimbrite starts, and what we see is actually the higher temperature part. And you can see how during the eruption, this goes from the base of the pyroclastic flows to the top. You see this red cluster that progressively disappear, and you get more and more of the lower temperature material. So there is a feeling here that something is happening. So the first material that comes out record the deepest pressure, the highest pressure and lower temperature. So it's something coming at least from depth, because these crystals may be antecrystic or xenocrystic, but they need to be brought up by something. And then the reservoir is emptying, and we see perhaps the lowest temperature at the bottom of this. And this is the final eruption after the ignimbrite, and you see that it keeps erupting some of this high temperature material that perhaps was left over inside the reservoir after this eruption. So we did field work also to look at the carbonates. So one of the arguments to say that the carbonates are the assimilation of carbonates in the shallow crust is one of the drivers for the big explosive eruption is that when you go in the field, you see fissures like this one. So this is Pozzolane Rosse. You see this was a carbonate xenolith. Now it's filled with skarn, essentially. And then this unit, Pozzolane Rosse, is full of the gassing pipes. Now, one thing that when we went in the field was a little bit puzzling for us is how do you preserve an empty cavity in a big ignimbrite? There is 30-meter deposit here. And we were wondering why this thing didn't collapse. Plus the degassing pipes, they all start from this empty now reminiscence of carbonate xenoliths. So we started wondering if this actually doesn't happen in situ post-emplacement. The reaction between carbonate and this magma is very fast. This magma is very hot. They're in place at probably 1200 degrees or so. And to look at this more in detail, we went farther away. So we went to the Apennine. This is exactly the same eruption. And when you look at the carbonate xenoliths, they're almost pristine. And 99.9% are pristine. So they don't look reacted at all. So are they just xenoliths? And this is eruption that happens after. Also, I have to say that Pozzolana Rossa is the one that contains a lot of these xenoliths, but many other eruptions don't show, I mean, have the xenoliths, but they are not reacted, and they have much less. So why it should be a common process? So this is where we started a little bit to question this. So now we start to look at the Villa Senni. This is the last large ignimbrite. So this is the sequence. These are the formation we looked at it before with Mónica. These are the eruption that precedes the ignimbrite. You see a paleosoil here, another sequence of fall deposits. Then there is another large paleosoil, and this is the Villa Senni. This is the fall deposit part, and then the pyroclastic deposits. This is a Tuscolo. We did some Clinopyroxene stratigraphy. This is what we see. If you look at the pyroxene on the fall deposits, they have up to 1% of chromium, and they have the magnesium number of these objects is between 92 and 96. That is very high. And then going up stratigraphy, we see how this high chromium pyroxene tend to disappear. And so it looks like the most mafic stuff came out first, and then the later material came out later. The most evolved material came out later. So this, we think, tell us something about the trigger mechanism for this eruption. So when we did the thermobarometry, this is now putting all the data together. This is Villa Senni 0, and these colors are for the other units. You see the same thing. The Villa Senni 0 is the largest. And what we find the most interesting, and when we saw this, we thought our thermometer was just giving random numbers, is that the highest chromium and highest magnesium clinopyroxene record the lowest pressure. So this is what I was speaking at before. If this magma comes directly from the mantle, the first chance it has to crystallize is in the shallow crust, when the magma is then water saturated. If this is the case, then the composition of the pyroxene that crystallized from this mafic material will be chromium rich and magnesium rich. So we think that this high chromium, high temperature, and high magnesium is the trigger of the eruption. This is magma that comes up straight from the mantle and brings up with it a lot of this antecrystic or xenocrystic material that was distributed throughout the crust while the magmatic system was being built up. So to tell you the truth, when we saw this, we started to make a parallel between Colli Albani and a kimberlite. So we think that magma in this volcano is transferred very rapidly from the mantle to the crust. And this is what brings up a lot of this material. And this is where I started to see parallels with the Eiffel, where I still remember the big amphibolite xenolith that Schminke was showing one of the first meetings we had in this group. And he said, this stuff is deep. So phreatomagmatism, that it was one of the things he probably invented, said maybe it doesn't work as I said at the beginning. So when we look at the isotopes, we did some isotopic. So these are this is the work of Conticelli, but Conticelli is arguing essentially that the contamination happens deep, and a lot of it is a problem of mass balance. He said to explain the composition of the Roman province, it will take 75% of shallow carbonate assimilation. This is obviously too much. It will take a humongous amount of it. The magma will change composition. So he thinks that the contamination happens deep in a mantle that is veined with some fluids reacting in the lithosphere, and then the partial melting of this fluid during the stension and the Tyrrhenian area produce this weird composition. You see that the composition of these magmas isotopically is close to the limestone and marstones that are typical of the Apennine sequence. So what we did was to do isotopes with our Neptune in Geneva. We took the pyroxene with the highest chromium content and the highest magnesium content. So there is no high chromium content skarn pyroxene that can be generated. and we did the isotopes, and the isotopes are limestone and Mars. So this stuff that potentially comes from depth is already recording a lot of contamination or influence from these limestones, but we think this is a deep signal. It's not a shallow signal. Conticelli presented some other evidence. He measured nickel and lithium in olivine, and the content of lithium in olivine in these magmas is also very, very high. And this is another argument he uses to say the contamination is deep in the mantle. I will not go through this. This is a bit of detail about the work, but so what I did, I did some MELS calculation. We have some melt inclusion data that I'm not going to present, unfortunately, because we don't have standards to confirm if our measurements were good enough. We did some melt inclusion measurement in pyroxene, and we obtained up to 3.5 weight% of CO2 in this melt inclusion. That is very high. The problem is we didn't have standards, so we are not comfortable yet with presenting this. We hope to confirm the results at the beginning of next year. This is the case. This magma contains about 3.5 weight% of CO2 and 2 weight% of water. So what I calculated is the variation of volume as function of depth for a magma that has this with these conditions here, and that's the composition of Colli Albani. And you see that there is a large expansion when the pressure reaches about, I mean, at this is, I think, 200 bars, the volume has doubled now in terms of gas. So there is so much gas, even without considering any external input, the amount of dissolved gas is sufficient to produce a very large expansion of this magma, and the viscosity will not change. I mean, note, this is Pascal per second. This stuff is really low viscosity. So the point here I'm trying to make is that there is a lot of expansion. Magma comes up, probably the gas will even separate from the magma because the viscosity is very low. And there will be a lot of expansion, and this could be a potential trigger for an explosion and eventually then for a caldera collapse. So how we envisage this? This is again the work of Mónica. We think that during the build up to an ignimbrite, there is magma in the upper crust. So for the moment, there is no magma in the upper crust, so this will be good. We are not building up to an next ignimbrite eruption at Colli Albani. But you start to have pockets of magma in the upper crust, then eventually merge and produce a large reservoir. Then one of these bursts, if you want, of gas and magma comes up, start erupting, producing a subplinian or a plinian eruption, and eventually this destabilizes the reservoir, and we get a caldera collapse. Now, if you look at the final activity, we don't get caldera collapse, we get only this Mars here. And we think the reason is that the process is identical, and perhaps this was also happening in between or before the ignimbrite. But if there is no magma in the upper crust, there will not be caldera collapse. So we will have the formation of this Mars fed by these deep magmas rising very fast, but there will be no formation of caldera because there is no magma in the upper crust. And to form a caldera, there need to be magma in the upper crust. So this is what I was showing to Gerard at the beginning. It's a thin section. We just got it. This is a sample that we collected from the Albano Mar. And when I saw it, I was very excited because this looks like an awful lot of olivine to me. And I was saying, this is the first mantled xenoliths we get from Colli Albani. This will be the first. And we did a thin section, and this is how it looks like. And to my big surprise, this stuff here is not olivine, is a monticellite. That is the calcium olivine. This looks to me like deep. This xenolith contains melts. So Monday, we are going to analyze it, all the phases and the melt. I'm very excited. This could be, so my biased view say that this could be a witness of the percolation of carbonatitic melts into the lithosphere that make the lithosphere react and produce these veins. So that will be the first occurrence of this stuff, but I'm happy to hear your idea. So surely shallow level assimilation is taking place. There are a lot of evidence also from the gassing now in here, but I think there is geophysical evidence, geochemical evidence that are sufficiently good to say that this is not the driver of the explosivity at Colli Albani. We think it's a deep process. So the carbon dioxide is sourced from somewhere in the slab. And it is the rapid ascent of this magma that, similarly perhaps to kimberlitic pipes, magma rises extremely fast. There is a lot of gas, brings up a lot of material from depth. We have now a full suite of xenoliths from the Albano Mar. We are going to do thermobarometry. They look of an incredible variety. So I think they sampled the entire crust. So I don't think there is a way to think that there is magma coming up, interacting with some shallow water and producing this large explosion. And I think the only witness we have of this process happening is the last phase, because the previous phases where this was probably happen again has been totally erased by the caldera forming eruption. And that's it, I'm done. 1 minute delay.